So we move on to question number 3. In question number 3, I'll clear another conceptual problem or another conceptual theory that we have studied. Question number 3, I'll give you a statement and you give me or you tell me whether that statement is true or that statement is false. My statement is, in Alright, reversible expansion of ideal gas, work done is greater than irreversible expansion. Now, no. What do I mean by reversible expansion and irreversible expansion? And although we have talked in great length about this, but still I feel like to explain this one more. Now suppose I have a container, I have a gas, I have a piston like this. Now what I'm doing, I have pressed by my hand this piston so that the pressure of the gas is not pushing that piston upward. So I have some mechanism, either I have pushed this piston, I am pushing this piston by my hand, or suppose I have a clamp here that is not allowing that piston to come up. Now what I do is I remove this clamp. I put up my hand on it and I exert the piston from upward, and that is balanced by the pressure exerted by the gas from inside. Now slowly, very slowly, I allow this piston to come up. Very slowly. Now this process is going to take infinite time. Let's assume that after infinite time, slowly, very slowly, I allow this piston to come up, and then I remove my hand. So here I have a clamp. Anyway, this piston cannot come above this level. So this is a reversible process that goes very slow. Another way of doing this was, so wherever the piston was, suppose again I keep my hand over my piston so that the piston cannot come above that level. Now all of a sudden I remove my hand at once. So what will happen? Outside there is very small pressure of atmosphere, inside there will be a huge pressure of the gas. So there will be a immense pressure difference from inside and from outside. So due to that huge pressure difference, huge acceleration will be provided to the piston, and at very fast speed, impulsively, zoom, it will come and strike this clamp. This would be irreversible process, right? So this is what I mean, reversible and irreversible process. We have talked about this before. So this is reversible, which is slow. This is irreversible, which is very fast. Now in which process work done has been done greater. Now this problem will clear our concepts, and this problem will help us to make our concepts even stronger in this chapter and solve other numerical problems that are yet to come. So this is my statement. You think about it, in which case the work done should be greater. The one in which now work done, when we say work done, we mean work done by the gas, not by me, not by any other external surrounding. So remember, when we are talking about nothing is said by whom or whose work are we talking about. It is always implied we are talking about the work of our system, and I have already told you our system consists of an ideal gas. Alright, so let's proceed. Let's try to think, or rather you think, in which case work done will be more, and I'll give you an explanation in which case work done should be more. Now I'm assuming again, it would be can be a very gross assumption that you have thought and you are prepared with your answer. If you are just listening to it and enjoying my speaking, then that's not going to help you, my dear. You need to think on yourself. So better be prepared by an answer and then listen to it. Otherwise, go watch some song on YouTube instead of listening to it. So suppose before expansion the pressure inside was P1, the pressure outside is P0, or atmospheric pressure is P0. Now here also the atmospheric pressure is P0, and here also the initial pressure was P1. What I did here, I allowed the expansion to be very slow. Here I removed my hand or whatever clamping was there all of a sudden, and this piston came up with a huge acceleration. The process was very fast. So this means P1 is much greater than P0, or P1 is at least greater than P0. That then only the piston will come upward. That means the internal pressure has to be greater than external pressure. Then only the piston will go up. Otherwise it will move down. So we are assuming that piston is going up. That means the internal pressure is greater than external pressure. Now in this case, if I have to calculate work, now suppose the moment I remove my hand, what's the work? The moment I remove my hand, then the pressure, the resistance that piston is having is only the pressure which is there from the surrounding. That means the atmospheric pressure. So the only resistance this piston will have, the piston will have to go against pressure P0. So the work done in this case by the piston will be integral Pdv. This is always the work done. So here in this case will be integral P0 dv. The P0, because P0 is actually the pressure which is being exerted on the piston. Because this piston is going to move very fast. So this piston will go very fast and the gases all will remain inside towards the bottom. And after some time again the gas will gush upward. So actually this piston is having a resistance from the external pressure P0. So the P0 will try to force this piston downward, and against that force this piston will rise upward. So this piston is rising upward against pressure P0 here, and that P0 is the atmospheric pressure. Alright, now here the pressure is initially P1. I will slightly reduce the pressure from P1 to P1 minus a slight pressure. Then this piston will come slightly up. Then again I'll reduce that pressure slightly and it will come up slightly. Again I'm going to reduce that pressure slightly and it's going to come up slightly. So throughout the process I'm going to maintain a pressure very much equal to P1, and slightly gradually I'm going to decrease it. Here I decreased it all of a sudden. So throughout the process the pressure is P0. Here throughout the process the pressure is changing. So P1 dV is the pressure for a small change in volume. Next small work done will be P1 minus dP. Very small pressure will be decreased from P1, and into dV will be the next small work done. Next small work done will be P1 minus P1 minus 2 dP will be the next pressure into dV will be the next small work done. So as you can see, initial small work done was P1 dV. Here it will be P0 dV. Next small work done will be P1 minus dP into dV. That means this pressure into dV, and here again we are going to have P0 into dV, because in case of external irreversible process, throughout the process you have a pressure P0. So here the pressure is not decreasing, rather it is remaining constant throughout the process. Here the pressure is gradually decreasing, but still this gradual decrease in pressure keeps the pressure much higher than this case. So in this case pressure throughout is going to be large. In this case pressure throughout is going to be constant and much smaller than this case. So in this case the resistance provided to the piston against rise will be much higher than this case. So work done in case of reversible process is going to be much, or not much, even the work done in reversible case is going to be higher than the irreversible case. Alright, so the highest amount of work done will be done in case of reversible process, and the least amount of work done will be done in case of single step irreversible process. Single step because all of a sudden I remove the pressure and this is rising to the final height in one step. Otherwise what I could have done was I could have kept a clamp here, I could have removed my hand, so this piston would have moved in a single step from this position to this position, and again I would have removed a clamp, then in the next step it would have moved from this position to this position. So in 2 steps it would have gone to the final position. So it would have been 2-step irreversible process. Now we have seen the case of single step irreversible process. The bottom line is the work done in reversible expansion is greater than the work done in irreversible expansion. So work done by the gas in reversible expansion is greater than work done by the gas in irreversible expansion. Now these theories are very important. You must know these concepts, because what they do in exam is they will ask you to, in multiple choice question, they will ask you to choose or pick up the correct statement, and they'll give you 4 conceptual statements like this. So you must know these. So this is third problem, and I hope I did my best to make you understand this. So we move on to the fourth problem. The fourth problem is pretty easy, and we move on to the fourth problem. Suppose I have PV curve like this, and I have shown you 3 presses. One is like you understand, I hope, what we are doing here. I mean, there's a point at A here. This means my system is at A. Now my system has moved from A to B, and it has followed this path. Another path could be like this, yet another path could be like this. So let's see, this is path 1, this is path 2, and this is path 3. Now if I ask you in which path highest amount of work has been done, or arrange the work done in 3 paths in ascending order. So you need to tell me, or you need to arrange the work done in 3 cases in ascending order. Now how can we calculate work done? I haven't been given any information as such. What is the mole in the system, mole of the gas in the system, what is the temperature of the system, or through which process the state of the system is being changed, whether through adiabatic or isochoric or isothermal. I haven't been given any information. I have been given just PV curve. Now we have talked at great length before that PV graph is indeed very helpful, very useful. PV graph gives us lots of information. PV curve tells us work done. Now how does it tell us? I have given you explanation before. Since the formula of work is PdV, so it's in the form of y dx. So if when you plot the curve y versus x, then y dx gives you the area under the curve. So area under the PV curve is going to give you PdV, and work is PdV. So area under the PV curve is going to give you work. So area under the third process is this area, right? If you're going to find area and work done in the second process, then you have to see the area under the second process. Area under the second process will also include this area. So area under the second process is area under the third process plus this area. Area under the first process will be the area under the third process, or the area under the second process plus this area. So the highest amount of area would be covered under the first curve. So highest amount of work done will be in the first process. So in the third process work done will be least, and in the first process work done will be the most. That's it. This is easy one. So we move on to the fifth problem. Now fifth problem. Now work done. Work done we have found out. Work done in thermodynamics in this chapter, for this particular chapter, is always going to be integral PDV. Right? Now how it comes, we have seen how it comes. How it comes because we are using an ideal gas and we are using a cylinder and we are using a piston. So that force is converted into pressure and that dx is converted into dV, and we have seen that before. So work done is this. So the whole concept, the whole idea and the formula which we drew for the 5 process, we have seen how to get the formula. Actually this is the integral. Whenever we have to find the work, we have to solve this integral. Now to solve this integral, I can't integrate pressure in terms of volume. I can't integrate pressure in terms of volume. So what I do is I somehow bring the expression of pressure in terms of volume. Then I integrate it, as we have seen in case of adiabatic process and isothermal process. So suppose I have been given an expression for pressure and volume, and I have been said that P is equal to kV square. Now for ideal gas we know PV is equal to nRT. That's how pressure and volume are related. But suppose this is a special kind of gas or a real gas whose behavior is approximated to this expression. P is equal to kV square. K is some constant, and the constant of K, that constant value, the value of this constant is given as 6 bar per meter cube. Alright, now you have been asked to calculate the work done when there is expansion in the ideal gas from 1 meter cube to 3 meter cube. When this expansion occurs, then what will be the work done? So this is an easy, simple problem. In exams and even in IIT JEE, you can be asked this kind of problem. So what you do, you integrate. Now any ready-made formula will not be used because all the formulas that we have derived is using the expression PV is equal to nRT. None of them have incorporated this expression. So every formula that we have memorized from the book fails here. So if anyone does things like this, then there's a high chance that IIT JEE will do, and IIT JEE indeed have done in past. They will change the expression from PV is equal to nRT to something else. Then you become handicapped if you have mucked up things. None of the formula will be valid, and if you use those formulas, you will be the biggest foolish on the earth. So what we do? We use the basic. We derive the formula all over again. So what we do, instead of pressure, we generate an expression of volume, and from here it's hell lot of easy to generate an expression of a volume. So what we do, we replace P by kV square. So to integrate this, I am replacing P by kV square as I have been given. Now the whole thing is easy to integrate. K I bring out of integration because it's a constant, and V square dV is a cakewalk to integrate. The integral will be V cube by 3, and if you put the limit, the expansion is from 1 meter cube to 3 meter cube. So we put the limit from 1 to 3. That's how we do. So if you do it, if at all you do it, you will get that's what you will get. So you will get K into 26 by 3. Now you will have to put the value of K. So K is 6 bar per meter cube. Alright, so this, if you put the value 6 bar per meter cube. Now remember this volume, this is a cube of V. So here we have put the value of V with the unit. So the unit is meter cube. So if you put here 3 meter cube, and the cube of that will give you m ki power 9. Alright, and m ki power 3 will be cancelled from here. So effectively you're going to have m ki power 6. So I'm not writing that, but that is here you have indeed m ki power 6. So if you put just the numerical value 26 by 3, then this is easy to see that you are going to get 52. Now you will be trapped here and you will be finding yourself in a hell like situation if you don't know what unit you are going to get eventually, because if you see and if you analyze, we are calculating work and the SI unit of work is joule. Now the simplest and the most easy thing to get to the unit of the final quantity is, look, I want work in joule, and joule is a SI unit. So if I keep SI unit of everything in the expression, I'll get the SI unit always of the final expression. Suppose I'm calculating work, I want the SI unit of work. So what I do, I put the SI unit of everything in that. So here I have K and V. So what I'll do, I'll put the SI unit of K and a SI unit of V. So that is going to give me the SI unit of work. So I want to bring my work, because this is going to be a complex bar meter ki power 6 something. So or in exam, if you have a multiple choice question, the expression will be in joule. So actually you have to know how to convert this into joule. So bar, the SI unit of pressure is Pascal. So what you should do, you should convert this bar into Pascal. When you convert this bar into Pascal, and the SI unit, and you have to, and when you convert volume into liter, so that Pascal and liter is going to provide you the SI unit of work, which is joule. Alright, so when you do it, and this conversion factor, you must know that 1 meter cube is 1000 liter. So when you do it, and the conversion factor of bar and Pascal, I believe I have told you before, when you do it, you will get 5200 kilojoule. It would be really a shame if you will not be able to do it. You must do it, and if you don't do it, and if you just keep on watching, I wonder whom are you deceiving other than yourself. The answer would be 5200 kilojoule. You must work this out and get the answer. That will complete question number 5.